Linear Algebra II, Lecture 7, Kernel and Image. Let us start from the definitions. Let V and W be two vector spaces, and let F be a linear map from V to W. Definition. The kernel of F is defined as the set of all vectors V in V which ascend by F to 0. So the usual notation is ker F. Another definition. The image of F is defined as a set of all vectors f of V, where V is an element in V. So this set is a subset of W, and the usual notation is im F. For example, if f from V to W is the zero map, then all vectors of V ascend to 0, and therefore the kernel of the zero map is the whole original vector space V. And the image of this map is only the zero vector in W. Another example, if F is the identity map from V to itself, then the kernel of the identity map is 0, because only the zero vector is sent to the zero vector, and the image of the identity map is the whole vector space V, because every element in V is the image of something, namely of the same V, under the identity map. The first observation about the kernel and the image is the following proposition. Claim 1, the kernel of F is a subspace of V. So we know by definition that the kernel of F is a subset of V, and we claim that even more is true, namely that the kernel is a subspace of V. Similarly, by definition, the image of F is a subset of W. And now claim 2 is that the image of F is actually a subspace of W. So we will prove the first claim, and the second claim is proved similarly. To start with, let us note that the zero element of V belongs to the kernel of F. This is because every linear map sends the zero element of V to the zero element of W. Next step, if x and y are two elements in the kernel of F, then using the linearity of F, we can compute the image of x plus y under F. So f applied to x plus y is equal to f of x plus f of y. This is because of the linearity of F. So since x is in the kernel of F, f of x is 0. Since y is in the kernel of F, f of y is 0. And 0 plus 0 is equal to 0. So this means that f sends x plus y to 0. In particular, x plus y belongs to kernel of F. So kernel of F is closed with respect to addition of vectors. So this is the next step in proving that kernel of F is a subspace. And finally, let x be an element in the kernel of F and lambda be a real number. Again, using the linearity of F, let us compute the image under F of the element lambda dot x. So since f is linear, we can move lambda out, so this is equal to lambda times f of x. Since x is in the kernel, this is equal to lambda times 0, and everything times the 0 vector is equal to the 0 vector, so this is equal to 0. In particular, it follows that the kernel of F is closed under scalar multiplication with real numbers. So it's closed under taking the 0 element, it's closed under addition, and it's closed under multiplication with real numbers. So this proves that kernel of F is indeed a subspace of V. Next observation about kernel and image is that they can be used to determine such properties of a linear map as surjectivity and injectivity. So as before, let F be a linear map from a vector space V to a vector space W. Claim 1, the map F is injective if and only if kernel of F is 0. Claim 2, the map F is surjective if and only if the image of F is equal to the whole target space W. Proof. The second claim is basically the definition of the fact that f is surjective. So this is an easy fact. To prove the first claim, assume first that f is injective. Then, of course, kernel of f is equal to 0 because f is injective. It can send to 0 at most one element, and of course the 0 element of v is sent to the 0 element of w, so therefore kernel of f is equal to the 0 vector. Now let us assume that f is not injective. So this means that there exist two different elements x and y in v, such that f of x is equal to f of y. Let us then compute the image under f of the difference x minus y. Due to the linearity of f, this is equal to f of x minus f of y. But f of x is equal to f of y, so the difference between these two vectors is 0. In other words, this means that the non-zero vector x minus y belongs to the kernel of f, because it is sent to 0 by f. And therefore, the kernel of f is non-zero, so it contains a vector which is not a zero vector. So if f is not injective, then the kernel of f is not 0. And if f is injective, then the kernel of f is 0. And this completes the proof of the proposition. As an immediate corollary of this proposition is that the map f is bijective if and only if its kernel is 0 and its image is the whole target space. This is because f is bijective if and only if it is both injective and surjective. Let us now discuss the following important result called rank nullity theorem. Let f be a linear map from a finite dimensional vector space V to a finite dimensional vector space W. Then the dimension of V is equal to the sum of the dimensions of the kernel of f and the image of f. So dim V is equal to the dimension of the kernel of f plus the dimension of the image of f. Proof. Let v1 and so on vk be a basis in kernel of f. So we just choose some basis in the kernel of f. Then, of course, because of this choice, k is the dimension of the kernel. We know that the kernel of f is a subspace of V, so we can extend our basis in the kernel of f to a basis of V. So let's say this extension is v1 and so on vk. This part is a basis in the kernel of f, and then we extend by some vectors vk plus 1 and so on vk plus m. So then, of course, k plus m is dimension of V, because we just chosen a basis of V which consists of k plus m vectors. Lemma: the images of vk plus 1 and so on vk plus m under f form a basis of the image of f. We will prove this result on the next slide. But given this lemma, we immediately have that the dimension of the image of f is equal to m. So the dimension of kernel is k, the dimension of image is m, and the dimension of V is k plus m. So k plus m is equal to k plus m, which is exactly the formula in our theorem. So in order to complete the proof of the theorem, we just need to prove this lemma. So to prove that something is a basis somewhere, we need to prove two statements: that the elements of this set are linearly independent and that they generate the vector space. So first claim, f of vk plus 1 and so on f of vk plus m generate the image of f. Indeed, any element x in V can be written as a linear combination of our basis vectors vi's with some real coefficients ai's. So now if we apply f to this linear combination, using the fact that f is linear, so we can write f of this linear combination as the linear combination of f of vi's with coefficients ai's. But now the elements v1 and so on vk are in the kernel of f, so they ascend by f to 0. So the first k terms of this linear combination are just zeros, and we can write this linear combination as a sum over all I from k plus 1 to k plus m, ai times f of vi. And since arbitrary element in the image is of the form f of x, we just saw that we can write this element as a linear combination of our elements f of vk plus 1 and so on f of vk plus m. So this proves the first part of the lemma. And the second part of the lemma is that these elements f of vk plus 1 and so on f of vk plus m are linearly independent. Indeed, assume that we have some linear combination of these elements which is equal to 0. Using the linearity of f, we can write this in the following form, that f applied to the sum over all I from 1 to m, ai times vk plus I is equal to 0. But this means that the linear combination of vk plus 1 and so on vk plus m belongs to the kernel of f. But this means that this linear combination can be written as a linear combination of the elements v1 and so on vk. Moving everything to the left-hand side, it follows that we have a linear combination of all these vectors, which is equal to the 0 vector. But since all these vectors are linearly independent, they form a basis in V, it follows that all coefficients of this linear combination must be 0. So in particular, all our AIs must be 0, which establishes that f of vk plus 1 and so on f of vk plus m form a linearly independent set of vectors. So before we establish the next property, let us make a quick recap on the properties of the maps from a finite set to itself. So let X be a finite set, and let F be a map from X to X. Proposition: the following assertions are equivalent. The map F is bijective, the map F is surjective, and the map F is injective. So this is a property of a finite set. This proposition is not true if X is an infinite set. And the next application of the properties of kernel and image is a proposition which gives us a generalization of this proposition for linear operators on finite dimensional vector spaces. So here is a linear analog. The corollary from the rank nullity theorem: let F be a linear operator on a finite dimensional vector space V. Then the following assertions are equivalent. F is bijective, F is surjective, and F is injective. So to prove this, we actually need to prove only two things. We need to prove that surjectivity of F implies injectivity of F, and vice versa, that injectivity of F implies surjectivity of F. So let's prove this. So let us prove that surjectivity implies injectivity. So if f from V to V is surjective, then the image of f is a whole V. And now using the rank nullity theorem, the dimension of the kernel of f by the rank nullity theorem is equal to the dimension of V minus the dimension of the image of f. But the latter is equal to the dimension of V because the image of f is the whole V. And so the dimension of the kernel of f is 0. So therefore, kernel of f is a 0 vector space, and we know that this implies that f is injective. Conversely, if f is injective, then we know that this means that kernel of f is 0. Using the rank nullity theorem, the dimension of the image of f is equal to the dimension of V minus the dimension of the kernel of f. So the dimension of the kernel of f is 0, so we get dimension of V minus 0, which means that the dimension of the image of f is equal to the dimension of V. Since image of f is a subspace of V, and they have the same dimension, it follows that the image of f is equal to V. And thus, F is a surjective map. This should be F. So let us do some examples. Example 1, let F from R4 to R3 be the linear map with the following matrix in the standard basis. So the matrix of F in the standard basis is the matrix 1, 1, minus 1, minus 1, 1, minus 1, 1, minus 1, 0, 2, minus 2, 0. Find some basis in the kernel of F, find some basis in the image of F, and determine whether the map F is bijective or not. Solution. Let us start with a basis in the kernel of F. So an element V is in the kernel of F if it is sent to 0 by F. Writing this using the coordinate map with respect to the standard basis, we have that V is in the kernel of F if and only if the product of the matrix of F with the vector of coordinates of V in the standard basis, this should be 0. Please note that for the vector space R to the power k, an element of this vector space coincides with the coordinate vector of this element in the standard basis. So the coordinate map for R to the power k for the standard basis is the identity map. So therefore, in order to determine all elements V in the kernel of F, we simply need to solve the homogeneous system of linear equations whose matrix is exactly the matrix of F in the standard basis. So let's solve this homogeneous system of linear equations. So we start with the matrix of F in the standard basis, and we reduce it to a row echelon form using Gauss elimination. So here we have 1 in position 1, 1. We use it to kill this 1 in position 2, 1. So we subtract row 1 from row 2. Rows 1 and 3 remain the same, and row 2 becomes 1 minus 1 is 0, minus 1 minus 1 is minus 2, 1 minus 1 is 2, minus 1 minus minus 1 is 0. So now we have minus 2 here. We want to make it into 1. So we divide the second row by minus 2. The first and the third rows remain the same, and the second row becomes 0, 1, minus 1, and then 0. And now we can have this 1 and eliminate all other elements in the second column using this 1 in position 2, 2. So we subtract row 2 from row 1 and subtract twice row 2 from row 3. Row 2 remains the same, and row 1 becomes 1 minus 0 is 1, 1 minus 1 is 0, minus 1 minus minus 1 is 0, minus 1 minus 0 is minus 1. 0 minus 0 is 0, 2 minus 2 is 0, minus 2 minus twice minus 1 is 0, and 0 minus 0 is 0. So here we have our leading elements here in position 1, 1 and in position 2, 2. So we can choose x3 and x4 as free variables. And from the first row, we have that x1 is equal to x4. From the second row, we have that x2 is equal to x3. So for the free variables, we add the trivial equations x3 is equal to x3 and x4 is equal to x4. And now we can write the system in the vector form. So the vector x1, x2, x3, x4 is equal to x3 times the vector 0, 1, 1, 0. So these are the coefficients of x3 here, plus x4 times the coefficients 1, 0, 0, 1. These two vectors which we obtain, so this is a linearly independent set of solutions to our system. So these two elements form a basis in the kernel of F. So the vectors 0, 1, 1, 0 and 1, 0, 0, 1 form a basis of the kernel of F. And the next observation is that, again, in our matrix which we obtained after Gauss elimination, the leading elements are in columns 1 and 2. This means that in the original matrix, columns 1 and 2 generate the column space of this matrix. and the column space is exactly the image of F, because it consists of the images of the standard basis elements under F. Consequence, this means that the original columns 1, 1, 0 and 1, minus 1, minus 2 in the matrix of F, they form a basis in the image of F. As we have seen, the kernel of F is not 0, so the operator F is not bijective. And this finishes example 1. Example 2. Let G be a linear map from the space of all real polynomials of degree at most 2 to the set of all real numbers, given by the following formula. The value of G on the polynomial f of x is equal to the integral of f of x between minus 1 and 1. Let us find some basis in the kernel of G. Let us find some basis in the image of G. Let us determine whether G is bijective or not. Solution. In order to solve this problem, we need to compute the matrix of G. And for this, we have to find the values of G on the elements of the standard basis in Rx2. So the standard basis in Rx2 consists of the polynomials 1, x, and x squared. So if we apply G to 1, we need to compute integral of 1 between minus 1 and 1. That's obviously 2. The value of G at x is equal to the integral of x between minus 1 and 1. That is 0. And G of x squared is equal to the integral between minus 1 and 1 of x squared. So here the primitive function is x to the power 3 divided by 3. And since the integral is of length 2, we get that this is equal to 2 divided by 3. So this means that the matrix of G in the standard basis, so here's the standard basis consists of polynomials 1, x, and x squared, and in R the standard basis is just the real number 1. So the matrix of G in the standard basis is the following matrix 2, 0, and then 2 divided by 3. So in order to solve our problem, we need to do Gauss elimination and reduce this matrix to a row echelon form. Well, we have 2 here, we need to make it into 1, so we divide the row by 2, and we get the matrix 1, 0, 1 divided by 3. So again, we have the leading element here in the first row. So this means that we can choose x2 and x3 as free variables. And from this equation, we write x1 as minus 1 divided by 3x3. And then x2 is equal to x2 and x3 is equal to x3 for the free variables. So in the vector form, x1, x2, x3 is equal to x2 times 0, 1, 0 plus x3 times minus 1/3, 0, 1. So the vectors 0, 1, 0 and minus 1/3, 0, 1 form a basis in the set of solutions to our system. And now if we want to translate it into a basis of the kernel of G, we treat these elements as coordinates for polynomials in the standard basis. So this vector 0, 1, 0 corresponds to the polynomial x, and the vector minus 1/3, 0, 1 corresponds to the polynomial minus 1/3 plus x squared. So these two polynomials form a basis in Ker G. Also, the leading element in our row echelon form is in the first column, so the first column forms a basis in im G. So the real number 2 forms a basis in im G. But of course we can divide 2 by 2 and get that the real number 1 forms a basis in im G. So G is actually a surjective linear operator. But its kernel is non-zero, we just established it, so this linear operator is not bijective. So here are some problems and questions. Question 1. Prove with all details that image of F is a subspace of W. Question 2. Prove with all details that a map F from a finite set X to X is bijective if and only if it is injective, if and only if it is surjective. Question 3. Prove that a linear map F from R3 to R4 cannot be bijective. Question 4. Prove that a linear map from R4 to R3 cannot be bijective. And finally, question 5. Determine a basis in the kernel and in the image of the linear operator H from R3 to R4, which has the following matrix in the standard basis. So the matrix of H in the standard basis is 1, 2, 3, 1, 1, 2, minus 1, 1, 0, 2, 1, 3. Thank you very much and see you next time.